Okay, the second one is when the net force applied on the object is not zero. That means this body is going to move with some acceleration, like the one we just saw. Then the net force is always equal to the product of the mass and acceleration. Or we can rewrite as acceleration equal the ratio of net force over the mass. Again, both force and acceleration, they are vectors. And we can turn them into the scalar equation. We write them down as along each individual component. We can also have the equation there. All right, so the problems that for this type here, normally we see two kinds. First one, the problem gives us some information about the forces. Then we are asked to study the motion to find the speed, the distance, or the acceleration. The second type problem gives us some information about the motion. So we know how fast it moves, you know, if it moves, how long it stops. So those kind of information about the motion, we are asked to find the unknown forces. So depending on what we are given, we will be choosing either force equals ma, solve for A, or backward, given A, we solve for F, and be able to use those equations, you know, flexibly. Now let's look at a few examples. And again, so this one is a problem. What we are given here, no diagram is given to us. Read the problem carefully. We are given a car is traveling at some speed, and then the driver slams on the brake. So I start to the brake on. It skipped to a halt, stopped. The coefficient of kinetic friction between the tire and the road is 0.8. We know mu sub k. Determine the stopping distance. If the car is traveling either, you know, along slope up or downward slope, it is 10 degrees. So there are two problems now. Let's look at the first one. So let's assume that this car is moving upward. Okay, and along a slope. So let's quickly draw a sketch. So this is a 10-degree slope now, and a car is moving upward. And let's draw a car. Not a very good one here. So, okay, so let's see. So there is a car which is moving upward. And then at this moment, the brake is on. Okay, and then the car will keep moving until it fully stopped. We want to know from the moment the brake is on till it's fully stopped, how far it moves. And once the brake is on, we know what? We know the tire will not roll on the slope. And we will have, it will start to slide on the slope. And we are given the mu sub k. So write down what we are given. So we know m equals 1500 kilonewton. And we know what? We know initial velocity equals 30 meters per second. This is the kinematic information. And we know mu sub k equals 0.8. And angle theta equals 10 degrees. So this is what we are given. Now let's study the car. Once the brake is on, and while it is sliding, have many forces applied on it. Very, very typical along the slides inclined surface here. We still have the weight, mg. We still have the normal force, which is n here. And suppose it is moving upward here, then we know the friction force Fk is along the slope pointing downward. All right, so those are the forces applied on it. Now let's, pretty similar to the one we just saw. Now let's start to write down the equation here. Along y direction still. This is my x-axis, and I will use that one as my y-axis here. And if it is going up the hill, So this is the case one, up the hill. Then we know what? We know along y direction, sigma. So always I do the y. Why? Because y direction, there will never be any acceleration. The car will not leave the slope. So along y direction, I have normal force N minus mg times, so decompose the mg, and this is the y component. It will be mg times cosine theta equals 0. And along y direction equals 0 because there is no acceleration along y direction. And along x direction, very similar to the one we just saw here. And then we know the net force along x direction. We have the gravity is pointing downward. Friction is also pointing downward because I have made x positive to the right. Then both of the two forces, they should be negative. So I have negative mg times sine theta. Why negative? Because this component is pointing to negative x direction. And then minus what? Minus fk. So this fk equals mu sub k times n. This is my fk. Equals what? Equals ma. Does not equal to 0 anymore because it has some acceleration. Plug equation 2 to equation 1 to equation 2. So I solve n equals mg cosine theta. Then I get negative mg sine theta minus mu k times mg times cosine theta equals ma. Then I can get the acceleration equals m canceled. So this is the beauty of using the symbols. I really do not have to figure out, the mass time g, because see, mass, they got canceled out. A is equal to what? A equals negative. Okay, I have negative g times sine theta plus mu k times cosine theta. Now, what I'm going to do, I'm going to plug the number we are given. Do I know theta? Yes, 10 degrees. Do I know mu sub k? Yes, 0.8. Do I know g? I use 9.8. Then I can do the calculation. And I found this equals negative. Okay, I have my calculation done already. 9.42 meter per second. Squared is the unit for acceleration. So this is the acceleration when the brake is on. It has a negative. Why negative? Because it is opposite to the direction of the x positive direction. In another word, the car starts to slow down. But then we are going to work on the kinematics. So for this constant acceleration motion, what I have initial velocity equals 30 meter per second. And I know when it stops, the final velocity equals 0 meter per second. And it has this acceleration A equals negative 9.42 meter per second squared. I want to know the distance that it moves. Which formula can be used? Recall. So if you have the formula sheet, look this up, you should have this. So V final squared equals V sub 0 squared plus 2A delta x, or 2ax. This is the displacement. So if you have your formula sheet, look that up, because we know this one, we know this one, we know A. How do we find the displacement? So plug the number we have here, and for the one we have, the final velocity, V, so now we have V, the 0 squared equals 30 squared plus 2 times negative 9.42, because A is negative, times the displacement. delta x. 0 squared still 0. And then move this term to the left. We can solve for delta x equals 30 squared over 2 divided by 2 times 9.42. I believe the answer is around 47.8 meter. So that means when the car moves up, and then it will stop at 47.8 meters away. Okay, so if the question might be, if there is one barrier, or there is a person or who is crossing the road here is 50 meters away, will the car hit the person or not? We'll say no, because it will stop at distance of 47.8 meters. So we can expand the problem. This is the way. And what if the problem turns into, well, this car is not moving on a slope, it's moving horizontally. So theta equals 0 degrees. Or there is another one, second one here. What if the car is moving downward and still same initial speed and same condition, how far it will drive till it fully stops? So we'll do the same way. It just the direction of the friction force, when it moves down, it turns into opposite to the direction. It will pointing to the right along the slope again. Everything is the same. So I will not repeat the work. And for the inclined surface, you'll see the free body diagram, every single problem, they're so similar. Just we have the gravity, normal force, friction force. You just need to determine what direction of the friction force. If it moves up, friction force is down. If it moves down, then the friction force should be pointing up. And again, sum all the forces along y, sum all the forces along x, and only along y direction, sum of the force equals 0. Along x, this net force will not be 0 anymore. It equals m times a. Then we can get the acceleration. So this is the typical problem of given the force, find the motion. We can find the displacement. Example 3. Okay, and now let's look at the other one. Here comes another one. So what we are given, read the problem carefully. So we have a dog sled race and 2 ropes are attached to the sled and one on each side of the dog. So basically there were 2 forces applied to the dog. Or dog is pulling the sled. There were 2 tensions there. The sled rider together has the mass blah blah here, and then we start to run. It took the dog 15 meters to reach their cruising speed of 5 meters per second across. After the initial period here, then the sled or the dog will just run with the constant speed. But we are asked to calculate during this like initial period here, and we want to know what the tension in the ropes at the start of the race. So from the moment the sled was at rest till it reaches the speed of 5 meters per second. During this moment, during this period, what are the tensions in the ropes? Okay, and again, diagram. And what I'm going to do, so there is no slope. Okay, so I'm going to draw a horizontal line, represent the road here. And I'm going to draw a box, represent the sled and the person who is standing on the sled. And then, okay, you can put the dot, or you can just put the dot here. And we don't have to draw the dog because, and then we know the dog is pulling the sled. There are 2 ropes going around the dog. So I will put this force as 2 times T. So for within each rope, what the tension is. So the total tension should be 2T. And we also know what the angle is 10 degrees. It's 10 degrees above the ground. Rope pulls upward at 10 degrees. And we also know, so we have the gravity. So write down the given information. Mass equals 200 kilogram and the theta equals 10 degrees. And what else? We are given, so initial velocity is 0 meter per second. It starts from the rest. Then the final velocity V equals 5.0 meter per second. And during this period here, it moves by a distance of, so delta X equals 15 meter. So from the initial velocity to final velocity, totally it moves by 15 meters. Okay, and what else do we know? We also know mu sub k equals 0.06. So this is all the information we are given. Now we are asked to find what the tension T is. So again, finish the free body diagram. Not only we have the tension, we have the gravity, mg, we have the normal force, and what else? We have the friction force pointing to the left, F sub k. So totally, there are 4 forces applied on the sled. The pulling force from the dog, the normal force from the ground, the gravity from the earth, and also the friction force, kinetic friction force from the road. Okay, so that's what we have here. Now let's start to apply the equations. Where did the equation come from? Look for the net force. Before we look for the net force, again, put the Cartesian coordinate system. So X is horizontal because there is no slope now. Horizontal to the right, pointing up is my positive y direction. Origin is placed at the sled here. Now let's look at the equation. So along y, so I always prefer the y direction. Why? Because it's easier, because the sled cannot leave the ground. Therefore, the net force along y direction is always 0. So that get sigma Fy equals 0. Let's see, what equation do we have? Normal force and pointing upward. And then what else? Do we have another force along y direction? Don't forget this tension is pulling upward. It has a component. So decompose this 2t, the 2 rods, that's 2t here. Its y component equals, so it's positive 2t times sine. Again, I do not sum it up, use the 10 degree here. I just use the angle theta. I keep the symbolic expression, normal force, and plus 2t times sine theta, and then minus mg equals 0. So this will be my equation number 1. Okay, this is my way. I always start from the y direction. Why? Because the sum of the force along y direction is 0. And then along x direction, so sigma fx, do not write down this as equal 0. Why? Because it is not equilibrium anymore. It equals ma. So sigma fx equals max. Here, this is Newton's second law. Now let's figure out how many forces are applied along x direction. Point to the right is positive. I get 2t times cosine theta. Then minus Fk. And remember, whenever you have the kinetic friction force, you can use Fk equals mu k times n directly. So minus mu sub k times n. That's the Fk equals what? Equals max. And this is my equation 2. So having this free body diagram here, we can have those 2 force equations. Now let's see, to figure out what the T is. And we have to know what the acceleration is, because A is still unknown yet. How can we get AX? We are going to study the motion. We are given the motion here because, okay, so leave the 2 equations right here. Now let's look at the motion. We have initial velocity equals 0 meter per second, final velocity equals 5.0 meter per second. And we know the displacement, it takes the dog 15 meters to reach that speed. Okay, delta x equals 15 meter. And again, this equation is used so often. So v squared equals v sub 0 squared plus 2a delta x. You apply this formula here. Now we can solve for what? We can just put this on, do the substitution. 5 squared, 5.0 squared equals 0 squared plus 2a times 15. 0 squared is still 0. And are we able to solve for the a? So this a is a sub x along x direction. So now I can solve for the, based on the information of the motion, I can find the acceleration ax equals 25 over 30. If I do the calculation, it equals 0.833 meter per second squared. So starting from the information about the motion, I get the acceleration. Now plug ax to equation 2. Then I look at those two equations. How many unknowns do we have? We don't know n, we don't know t. So two unknowns, two equations. How can we get the t? So just the best way, substitute n from one equation to another one. So what I'm going to do now, I'm going to, so starting from equation 1 here, I can get n equals mg minus 2t times sine theta. Okay, so from equation 1, then plug it into equation 2, I get 2t times cosine theta and minus mu sub k times n. What is n? mg minus 2t sine theta. That is my n here. Equals what? Equals m times ax. Then solve this equation. So ax, I have a number. So for the t is the only unknown. If I keep working in the symbolic expression here, I get the t equals one expression of, so m ax plus mu sub, okay, not yet. I have the t here as well. Okay, so combine like terms first. I almost forget. Okay, so remove the parentheses, combine like terms. I get 2t cosine theta plus, so add one more step, so 2t cosine theta plus 2t times mu k sine theta. Then equals what? Move these terms to the right. max plus mu k mg. 2t, okay, combine the like terms. I get 2t times cosine theta plus mu k sine theta equals the right side. I have m times ax plus mu k times g. Factor m out. Then to get t, I got the tension equals, do the division. M times a sub x plus mu sub kg over what? Over 2 times cosine theta plus mu sub k times sine theta. Then let's check this expression. Do I know m? Yes. Do I know ax? Yes. Do I know mu sub k? Yes. Do I know cosine and sine theta? Yes. Everything is given. Then just now, you start to plug number in and use your calculator here. You can solve for t is about 143 newtons. So do the substitution. What I want to share with you here, so if you start to do the calculation at earlier, like do the plug the mgn, and you will involve with a long expression. You might have to multiply the mass and then divide the mass later. My recommendation for the problems for those when we do the analysis here. Let's always start with the symbolic expression, and after we solve for the final expression, and then we start to plug number in, do the calculation. It's easier to check your work, and also in case, like in the real world, we are doing some engineering problem, some condition might change. We don't have to redo the equation, resolve them, just update, like what if the angle now is not, if the dog, we shorten this rope, then the angle theta will not be 10 degrees anymore. It will be like 8 degrees. So we don't have to resolve the equation, just plug this new angle in. We still use the same expression. It can save a lot of time. All right, so this is a typical problem. See, we are given the information of the motion, and we are asked to solve for the force. The previous one is we are given the force. We are asked to solve for the motion. Those are the two general cases. And again, those two problems, the process is not very easy, but the idea is not hard. Always draw the free body diagram, get sum of the force, apply the Newton's second law. Those problems, I think they are straightforward. There is no tricks behind the problem. But when we are dealing with more problems, sometimes we got to be very, very careful. So some problems might have some hidden tricks there. We got to be very, very careful. So the next level, what I'm going to do next, I'm going to expose to you more complicated problem. And then we'll be gathering more experience. How do we work with them? So those first two, I call them general problems. Now let's see more complicated problems. Okay, again, this is about the force and motion, which means those bodies are not in equilibrium. For those problems, the commonly seen, the type 1 is, we call them combined bodies. So there will not be just one body there, one object. And for example, so there are two boxes, okay? They are connected by a string. They are moving together along a slope with the pulling force F. So those A and B, and they're combined body. And there is another typical one here. We have a pulley, and around the pulley, there are two meshes are connected or attached to the string respectively. And then if we, depending on its frictionless or there is friction here, the motion of those two bodies, they will in different way. There is another, I didn't have the diagram right here, so that will be, maybe we have a slope, and at the slope here, we have, again, a pulley right here, and a box is attached to a string, and string goes along a pulley, and then we have another mesh coming at the other side. This M is lowercase m. So anything, so these ones, those bodies, they are connected by strings. And remember, string can only provide tension. They cannot provide a push force. And all the cases, we always assume the springs, or the strings, their length is constant. They cannot be stretched. So those strings, their length will remain constant. In those cases, okay, so we will apply the third law, the Newton's third law, the tension between the two bodies, okay, which is pulling A or which is pulling B here. If we look at the internal tension, their action and reaction. So the tension on B and the tension on A, they are opposite, but same magnitude. Tension, their action and reaction. But we always think those two, if the string is stretched, those two bodies, they move with the same acceleration. So those two bodies will always move with the same acceleration. This A is moving to the right, this mass is moving to the right, and this is moving down, but because the length of the string cannot change, so those two will still have the same magnitude of acceleration, even though this one is going down, this one is going to the right. And this one is along the slope, this one is going down. When they are connected by the string, they always have the same magnitude of acceleration. I don't see they have the same acceleration. I see their accelerations have the same magnitude. So this is a very typical combined body. And there are more, okay? So the one block is placed on another one, and this force is applied on B. And then we know the friction force between A and B will make A move with B, or maybe it's sliding along B. We don't know what exactly going to happen. So those two things, when we see the body like this, sometimes we can treat A and B as one body. Sometimes we cannot, depending on what? Depending if there is any relative motion between them or not. So that will be even more tricky. We'll see that later. And the other type of problem we see will be a string is involved. So a string is connecting two bodies. And we normally ignore the moment, okay, or the period when the string is stretched. For example, so this A and B, they're connected by a string. A force is applied and is pulling both of them to the right. And so when we're studying them, we just see now the spring is fully stretched. It does not stretch anymore. It will keep that constant stretch. And then for that case, A and B, they can be seen as one body. Why? Because they move with the same acceleration. They can be seen as one body. And this other one here, okay, and the string is holding the B here, and both of them, they are moving forward. So we do not start from the moment the string is at equilibrium. So we skip that moment. We just look at the period. The spring has been stretched already. And so there's another case when a cart is moving to the right with some acceleration, and then the string is stretched to make sure the A is also moving with the same acceleration with the cart. And this is another moment, another example, like a body is resting on the string. Okay, so for all those combined body right here, normally we have two ways or two methods to study them, depending on what do we want to know. The first method, we call it unity method. So this is actually working for if all components within the system, they are moving with the same acceleration or no acceleration, they're resting together. Then we'll treat the entire body, we ignore the tension, ignore the strain between them, ignore the spring between them. We treat everything as one body. And in this case, we only look at the external forces. We don't care about what the strain force between them. We don't care, but that's internal force. We only look at the external forces. The other case, if we want to know what are happening between the components, or in another word, we want to know the interaction among the components, we have to isolate the components. This method is called isolation method. Like if we break that up, then isolate any part of the system, draw the free body diagram on it, then we'll be able to find the interaction among the components. So this is called isolation method. Which ways do we use? It depends on what is given, what is asked. So we have to, like, the more we do, the more experience we will have. We can choose the method quickly and correctly. Quick example 1. So no calculation, just a quick symbolic analysis here. F is applied to 4 identical blocks. So 1, 2, 3, 4 identical means they have the same mass, they have the same contact between themselves and the supporting surface right here. And we are also given the surface is frictionless. So that means no friction force is involved. Now we are asked to find the force between block 1 and 2. So see, apparently we know when the force is pushing block 1, 1 is pushing block 2, 2 is pushing 3, and 3 is pushing 4. So this is continuous, the force is passed on. We just want to know what are the interactions between block 1 and 2. So for this one, how do we do? So first, when we see this problem, we all know there is no way those 4 blocks move in their own way. They move together because they're against each other. So for this one, apparently all components will always have the same acceleration. I will treat all of the 4 blocks as one body, then apply the second law to it. So the total force applied on the system is what? Is F. And F equals MA. What is M? If each one has a force M, so this M, and M here, the total mass will be 4M times acceleration. This is one direction here. We don't have to write the vector notation. So F equals MA, M total. This is M total. Then what I get? I can get, so the acceleration for the system equals F over 4M. Then if I want to know the force between block 1 and 2 here, I'm going to isolate. Isolate what? I can either isolate the block 1, I can also isolate 2, 3, and 4. So both way works. I prefer to look at 2, 3, and 4. 2, 3, and 4. So they're still staying together. And see, have many forces applied on those 3 blocks. And of course, we have gravity, we have normal force. Okay, so along y direction, there is no concern. Along horizontal direction, how many forces are applied on 2, 3, and 4? Externally, there is only the force coming from block 1. So block 1 is pushing block 2. What this force? We don't know. We let it be F1. Is there any other force? No. So F is not applied to 2, 3, 4. But block 1 is giving a force to 2, 3, and 4. So this force is unknown. We let it be F1. So now look at what is the sum of the force on this new system. Vertical direction, those 2 cancel out. Horizontal direction, the net force will be just F1. F1 equals what? F1 equals now the mass for this new system, which is 3M now. 3M times what? Times A times A. Does the acceleration change? No. So the whole system is moving with this acceleration, and part of that also has the same acceleration, so times A. This A is the A we have here. Now plug A into the expression. So 3M times what's the acceleration? F over 4M. Then M cancel out. I get F1 equals 3/4 F. If we keep the same idea, so within this block system here between M1 and 2, the force is 3/4 right here. So this is 3/4 F here, and between 2 and 3, keep the same idea. Now we are going to look at 3 and 4. So actually we can get this force equals 1/2 F, and this force is 1/4 F here. So the force, total force, is kind of distributed based on the weight. When we just have one block 4 there. The force to push it will be just a quarter of 4 F. When we want to figure out what is happening between 2 and 3, the force will be, so those 2 blocks is half the total mass, so the force will be half as well. And between 1 and 2, that's 3/4 F. How can we get this? This is coming from the method of unity first. The whole system is moving with the same acceleration. Now I'm going to use the isolation method. No matter where I want to figure out the force, isolate the part, then draw the free body diagram. Get the force, force equals, again, for this new system, we still have total force equals total mass times acceleration. But then we are going to use the acceleration we get from the previous step. When we look at the entire body using the unity method, then we can solve for this unknown force. Very, very typical. So no number, no value here, but we still get the expression. So this is quick example 1. Quick example 2. So this is a string system. So a string are connecting 2 blocks. So those 2 blocks are connected by a string. And we know MA, MB, they do not have the same mass. Does not matter. MA is 2 times MB. They are sliding down on a smooth surface. So there is no friction force between the blocks and the surface here. We need to find the tension and also the acceleration. So there are 2 questions here. What is the tension between the 2 blocks? What is the acceleration of them? Okay, so we have seen the inclined slope so many times already. Same thing here. So I know when the 2 things, they are sliding down because of the string cannot be stretched anymore. Both of those 2 should move with the same acceleration. So I'm going to treat both of them as one system and then draw. So for this one, I'm going to redraw the diagram because I used the dot to represent both of them. Draw the free body diagram. Gravity, normal force, and do we have friction force? No, so only 2 forces applied on it. Then we are going to decompose this, the total M, and this is total N right here. Now let's solve for what is the net force along the slope right here. So we know along the slope, after we have seen this many examples already, I can get to the net force is along this slope direction. You can call it X, okay, equals the magnitude equals mg times sine theta. The net force equals m times a. So both of the 2 blocks here, does not matter what the m is, the acceleration is always equal g times sine theta. And it is moving along the slope, sliding down. This is the magnitude of the force. Then if I want to find the tension between A and B, what do I do now? I'm going to cut A and B. I only look at the point B now, or block B. Now, if I use the isolation method for block B, still I have the gravity is mbg. I have the MB right here. And then I have this tension, this T, and I know what? I know this MB is moving with this acceleration. So now if I write down the net force, so apparently the net force on B equals what equals block B only. Okay, so now I do not have too much room right here. When I look at B only, the net force along the slope equals T pointing down. So I make this direction be positive. T plus the magnitude of the weight is component along the slope plus mbg times sine theta. So this is the total force. Total force equals the mass of B times the acceleration. And we have found acceleration is g sine theta. So this is the A we get it from the previous step. So net force equals MA. Now when we compare the equation, we found this term, they're identical. Then we got what? Tension equals 0. So actually, this string is not pulling B, it's not pulling A either. When they are both moving with the same acceleration, the tension within the string is 0. And what is the acceleration? Equal G times sine theta. This is for the case when the two things they are moving along a smooth surface here. I will leave the question to you. What if we are given non-smooth surface, but the coefficient of the friction, kinetic friction, okay, between A and slope B and slope, they are the same. So everything, all the conditions are the same. Then what the tension and acceleration is. Okay, so if I know this mu sub k, this mu sub k as well, I leave the question to you. You try to follow the same way and derive the tension between A and B. So this is a quick example 2. Quick example 3, applied to a special case. So when we have one special moment, a string is cut suddenly, and what are happening to the system. So what I want to see now is string and spring, they're different. A string and a rope and a cable. So once we cut them, the force in them will disappear right away. So a broken string, a broken rope, they cannot provide any tension. But you know, when when a spring is stretched, the spring force will not disappear right away, because if it is stretched, the tension or compression in it only depends on my current deformation. And the string got to be when we look at the string, we got to be very careful. So typical example like this, we have a system like here, string and spring, they are supporting two mass here. So MA and MB, they are the same. They have the same mass here. So it is an equilibrium of the case 1. So look at the case 1 now. Now, at the moment, string 1 is cut. So this number 1 right here. So when the string was cut from 1, we want to find out the instant acceleration of the two masses, A and B. So this 1. And the second example right here is, so they are arranged in another way. String is on the top. We want to figure out what are the instant acceleration A and B if we cut from there. Okay, so now let's look at case number 1. I call this case number 1. Always, so for this suddenly cut problem, we start from before the moment when the string is cut. What are the forces in each component or in the string or the spring which are connecting the components? So for string 1, for case 1, before I cut the string 1 here, let's see, what are the forces in the spring? So quickly, so before we cut it, can we figure out the string force? String is supporting both of A and B. So Fk right here equals, so this Fk equals 2mg. What the force within the string A and B before we cut it? So this force equals 1 mg. So having this in our mind now, okay, this is the before we cut it. Now, after we cut the string, let's look at the A first. So now I move the sketch to here. So the string is right here. This is part the MA. When we cut the string, we know what? The string force disappears right away. Let's draw the free body diagram on particle A or mass A. How many forces now after we cut here applied on A? Always we have the weight, the mg, so that's ma and mb, they're both equal to m, okay? And what else? We have the strain force. And we know the strain has, the spring has been stretched already. When we cut this one here, the spring does not have time to recover yet. So the spring force is still maintained the same as before we cut the string here. So the spring force Fk is still equal to 2 mg, but it is pointing upward. So that's the moment, this case 1. When we cut the string 1, what are happening on A now? There is a gravity force, no tension anymore because the string is broken, but there is a spring here. The spring is still holding it with the force 2 mg. Now let's figure out what the total force, what the net force on A now. This 2 mg pointing upward to be still, that's the pointing upward is positive. Having this in our mind here, and we have 2 mg minus mg. That's net force equals what? Equals MAA. Can we solve for the AA? So 2 mg minus mg, that's mg equals MAA. So then we got AA equals G. It is positive. It means what? It means it is along the positive y direction. Okay, so this is for A. Now let's look at B. At the moment, when we cut the string here, how many forces are applied on B? There is only gravity here. The tension is broken. Nothing is holding it. So the net force on B now, so F net equals mg, but equals negative mg. Why? Because this is pointing downward with the negative y direction. Equals what? Equals m times AB. Then m cancel out. We get AB equals negative G. Negative means what? Negative means it is pointing downward. The magnitude is still G. So after we cut the string from 1 here, both A and B, they have one acceleration with the magnitude of G, but A has the G pointing upward. It will start to move upward with this acceleration. And B will fall with this G as acceleration, pointing downward, even though they have the same magnitude, but they have the opposite direction. This is for the first case. Now let's look at the second case. All right, so now let's see, before we cut it, is the string stretched or not? Yes, the spring is stretched. It is holding the B here. So I know within the spring, there will be one internal, the tension, Fk equals 1 mg. Why? Because it is only holding one mass here. The other case is holding 2 masses. So the spring force is mg. Now, after we cut to here, let's look at A. So the particle A or mass A, how many forces applied on it? I do not have enough space. Okay, I hope. Okay, there was some room right here. So draw here. This is the A. Are we able to figure out how many forces applied on A after we cut the string? Always there is one gravity, mg. Okay, this is coming from the Earth. It has nothing to do with anything else. What else? No string on the top, no force from the top, but it's still stretched by the spring. So the spring still keeps that force, mg, which is pointing downward. This is Fk, and this Fk equals mg. So the total force applied on A equals mg plus mg pointing downward. So what is AA now? So AA equals 2g or negative 2g pointing downward. right? That's the total force applied on it, spring force and gravity. And now let's look at B. When we cut, that don't matter. So we cut here, let's see what are happening on B. So think about this. B has the gravity. What else? It has a spring force, which is pointing upward. At the moment, this screen is cut. It does not affect the gravity. It does not affect the spring force. The spring force is still upward and the gravity is still downward. And those two happen to have the same magnitude. The resultant force is 0. So therefore, AB equals what? AB equals 0. All right, I hope you get some sense that when we are analyzing some special moment, when the string is cut, the tension disappears right away. But the spring will not recover right away. The spring force will remain there. So that will be another quick example. Okay, so let's see. One more quick example here. Okay, it's very challenging. So this one is very interesting, this problem. What do we have here? We have a long block M1 is resting on a smooth surface. Block M2 is placed on block 1, where the coefficient of friction are some constant. So we know we might have mu sub S, we have mu sub K. There's some constant here. Then a force F equals KT starts to work on M2. So this force is not a constant. This force is changing with time. It is a function of time. So F equals KT is applied on M2. And we want to see which diagram shows the change of A1 and A2, the acceleration for block 1 and block 2. So that's just based on the problem we are given. Let's draw a diagram to describe it. So we have a smooth surface and a long block. So we have a long block. This is M1, okay? And then another block, M2, this is M2. It's placed along on M1. So at the beginning, they're both resting on the smooth surface. Now a force F starts to work on M2, not on M1. So now we have this force, F equals K times T. Okay, so remember, this is not a constant. F is a function of time. And we want to know how does A1, the acceleration of block 1 and block 2 change. Let's think about what are happening. So once the force is applied on it, we know the force is increasing gradually. And when the force is less than the maximum static friction force between block 2 and block 1. So we are given, so mu sub S and mu sub K, they are they're given here. When the force is less than the maximum, Fs maximum, what happens? So the friction force, the static friction force between block 1 and block 2 will make block 2 stick with M1. They will be moving with the same acceleration. So when F is smaller than Fs, which equals mu sub S times M2G. So this normal force equals M2G. When that case, so F equals KT, T equals 0, F is 0, T equals 1, then we'll multiply by the K. So when this happens, M1 and M2, they are moving with the same acceleration. In other words, there is no relative motion between block 2 and block 1. And what is the acceleration? So that will be, so whatever this force is, I can treat block 1 and block 2 as one body. F equals M1 plus M2 times A. A1 and A2 are the same. And this F equals what? F equals KT. So therefore I can get A equals K over times T over M1 plus M2. Now let's see, A1, this is A1 and A2. So they have the same value. They're both equal to a function of t. And what is this function? A linear function. So we get a linear function and changing from 0 to some number until the friction force gets to maximum. Then block 2 start to slide along block 1. Okay, so at beginning. So now we'll see, well, all of the 4 diagrams, they have a linear from 0 to some, so I cannot tell which one is wrong. So they're both okay from t equals 0 to some moment, linear equation. Now when, so that moment, when M2 starts to slide on M1, then what is the force between block 2 and block 1? It turns into the kinetic friction force. So for block 1 now, so I know block 1, the friction force between block 1 and 2, it turns into F kinetic friction, which is equal to mu sub k times M2G, because the normal force is always equal to the weight of the block 2, mu k M2. And so in this case, this force, now we'll look at the block 1 now. This block force, block M1, have many forces applied on it horizontally. That's the only force applied on block 1. So for block 1, for M1, the net force is Fk. So we got mu k M2G equals what? Equals M1 times A1. So for block 1, net force equals its own mass times its own acceleration. Then I get the expression of A1. So A1 equals mu k M2G over M1. This expression has nothing to do with time. There is no t here. So which means A1 equals a constant. So now I know after block 2 start to slide on M1, M1 will have a constant acceleration. And when I go back here, I see A1 is constant. So C and D, they're gone because C, no, oh, C is gone. So A1 is not a constant. So A1 is constant, A1 constant, A1 constant. So A, B, D, some one of them might be correct. We have to look at what A2 is. Okay, so now let's continue to look at M2. So I have M2 sliding on M1 now, and I know what? I know the friction force between M2 and M1 now. It is, okay, it is the mu sub k times M2G. All right, so I have, if I look at M2, the net force horizontally applied on it equals what? Equals mu k times M2G equals the M2 times A2. Okay, the net force applied on M2. I'm looking at M2 now, isolation method. M2 has the force applied on it, which is the kinetic friction force, mu k M2G equals M2 times A2. So now can we get the expression of A2? A2 equals mu k times G. Okay, wrong. What else? I forgot there is a force. Okay, it's still pulling it. So the net force, okay, I just figured out, I just made a mistake. The net force applied on block 2, there is not only the friction force, don't forget we still have the pulling force. Sorry. Okay, so the net force is actually F pulling force minus mu k. So mu k, okay, yes, this is Fk. It's point to the left, minus mu k M2G equals M2 2a2. And what is this F? F equals KT. So F is still a function of time. We got F equals, so KT minus mu K times M2G equals M2A2. Now we got the expression of A2 equals, okay, divided by M2, we got, this is K over T divided by M2 minus mu K times G. This is the expression of the acceleration for block 2. So don't forget, so at the beginning I forgot, I made a horrible mistake. I forgot the force is still applying, is still pulling it. So the net force equals this. I get the expression. Now let's look at A2. It's still a function of T. This is a linear equation because mu K times G is a constant. Then A2 over time, we still have a straight line. The slope is K over M2. And then see, look at A and B. So A2 will be changing, will be a straight line. It has a slope, but A and B, which one is the right answer? Okay, both A2 now, they are straight line, but which one? Let's look at the expression here. So we all know that for any linear equation, we have the coefficient represent the slope. We also have another term. This term represent what? Represent the y-intercept. This is the intercept. So for the A2 diagram, what is its intercept? It equals negative mu K times G. So its intercept should be a negative number. Then we go back here. So A and B. If I extend this A2 diagram here, its intercept is positive, but this one is intercept is negative. So that means A is the right answer. So this one is a pretty challenging one, but I think it explains very well what the role does friction force play. So at sometimes, if there is no relative motion, then the friction between the two bodies, they're static. The static friction will respond to the external force. But when the body starts to have the relative motion, when one starts to slide on the other one, the friction force turns into a constant. So we have those expressions right here. So if on one problem, I do not just give you the symbol, I might give you some real coefficient number. I might give you the mass number. Then you have to be able to calculate what the acceleration is. Okay, so this is a very, very typical problem, which not only involves the multiple components body, the friction force is very important as well. How do I know? Is the force kinetic friction or a static friction force? And how do I know the direction of the friction force? We have to, look into the problem, look at the moment. So for this one, okay, this is one of my favorite problem. The commonly seen the combined bodies, those two blocks, they might work together, move together. They might not. If they're not moving together, then each one of them have their own acceleration, like the one we have here. But before there is a slight or relative motion between them, both of them, they will move with the same acceleration. So A is the right answer. This is what I see the challenging problems. And what I have here, let me check the time. It's 4 o'clock. Well, I will stop here today. And tomorrow we have more time.